Okay, here's a video solution for the 3.1 practice number 1. The first questions, I think there are 4 questions that ask about finding a greatest common factor. So let's remind ourselves what that means. So a greatest common factor is just the biggest thing that's going to divide evenly into each of the terms. Now we're going to be using examples. All the examples we treat are going to be trinomials, meaning they'll have 3 terms. But this same concept could apply to binomials with 2 terms, or later on in the class, polynomials with more than 3 terms. So the greatest common factor then, the biggest thing that'll divide evenly into all 3 of the terms. Another way of thinking about that is, which means exactly the same thing, but just an alternate way of looking at it would be, what's the biggest thing that we could undistribute from all 3 terms? So there's a couple rules we want to make sure we're always following. We know that when we write the trinomial in standard form, so the biggest power of x comes first, that's the leading term. We always want the greatest common factor to have the sign of the leading term. So in this case, it'll be positive. And then the other thing we can do is we can always break it into 2 parts, the number part and the variable part. The variable part is the easiest. The variable part of the greatest common factor is going to be the smallest power of x of all the 3 terms. We could call it the greatest common power of x, but really all that is of the 3, it's the smallest power of x. Well, in this case, the 40 doesn't even have an x, and so there is no x included in the greatest common factor. So it's just going to be the numerical part. So then we just have to find the biggest number that divides evenly into 72, 56, and 40. And how you go about doing that really is up to you. You could write out a factor tree if you want to. I think none of the numbers I'm going to give you are going to be so outlandishly large that just by knowing your math facts, you couldn't find them. So let's see, in this case, seems to me that the biggest number that's going to go into all those is going to be 8. 8 times 9 is 72, 8 times 7 is 56, and 8 times 5 is 40. Here's how we can know if we got it right, though. This trinomial is then going to be equal to 8 times what when I undistribute the 8? Well, let's find out. 8 times what is 72x squared? 9x squared. 8 times what? Better give myself a little more space here. 8 times what is negative 56x? Minus 7x. And then 8 times what is negative 40. So we got the expression 8 times the quantity 9x squared minus 7x minus 5. So 8 is our greatest common factor if there's nothing else I could undistribute, and there's not. There's no number that divides evenly into 9, 7, and 5, and so we're done. There's nothing else I could undistribute, and so the greatest common factor is 8. Okay? Okay, I'm going to skip to number 4. Same kind of problem. So this time we can see that because the leading term is negative, we already know that the greatest common factor is going to be negative. Let's start off with the variable part. What's the weakest power of x? Well, that's going to be an x squared. So we know that we're going to get an x squared is going to be the variable part of the greatest common factor. The number part is just the biggest number that divides evenly into 77 and 14, and that's just going to be 7. So negative 7x squared is the greatest common factor. If we were actually factoring this expression, which is why we would find out what the greatest common factor was, what we would end up having left over then when I undistribute the negative 7x squared is what? Well, negative 7x squared times what is negative 70x to the 4th? Well, negative 7 times positive 10 is negative 70, and x squared times x squared is x to the 4th. negative 7x squared times what is negative 7x cubed? Well, negative 7 times 1 is negative 7, so we don't need to write that coefficient, but x squared times x is x cubed. So negative 7x squared times positive x is negative 7x cubed. And then finally, negative 7x squared times what is negative 14x squared. Negative 7 times positive 2 is negative 14, and then x squared times 1 is x squared. So the answer, if we were to write this in factored form, would be this product. However, this question is only asking for the greatest common factor, which is negative 7x squared. Okay, got it? Okay, I'm going to skip those sign rules for factoring. That's no big deal. Okay, factoring simple quadratic expressions. No big deal.
Can I take 5, sir?
You may. Okay, so factoring simple quadratic expressions. And what do we mean by simple? That just means that the number in front of x squared is 1. So if the coefficient of x squared is 1, then remember how we do this is if it factors, we're just really undistributing by factoring, right? And we know that it's going to have to fit this template, because if I were to multiply these two factors out, when I distributed, x times x would give me my x squared. The question is just, are there magic numbers that make the rest of it work? And so we're going to start here, and then we're going to ask ourselves, can we find magic numbers that are going to multiply to negative 90 and are going to add to 1. So they're going to multiply to the constant and add to the coefficient of x. So we know, let's think about the signs of this then. If the numbers are going to multiply to a negative number, that means that one would have to be positive and one would have to be negative in order to multiply to a negative. And if they're going to add to a positive, that would mean that the bigger of the two would have to be positive. So we'll write the signs in, and then let's see if we can find the numbers. Well, yeah, positive 10 times negative 9 would be the two magic numbers that would work. They'd multiply to negative 90 and add to positive 1. So all they're wanting us to do here is write that expression in factored form, so that way. And it doesn't really matter which order you put these factors in. Makes no difference. Okay, another one. Once again, see if we can write this in factored form. Well, there's our template because the number in front of x squared is a 1. Question is, can we find the magic numbers? They've got to multiply to the constant, which is 80, and add to the coefficient of x, which is negative 18. Well, if they're going to multiply to a positive and add to a negative, we know that the numbers must both be negative if they exist. So are there numbers then that multiply to 80 and add to 18? Yeah, 10 and 8. So there's our answer, x minus 10 times x minus 8. Okay, and then what would this one be? If it works, let's see, if they're going to multiply to positive 90 and add to 19, they're both going to be positive. And then what would the numbers be that multiply to 90 and add to 19? Well, 10 and 9. Okay. Now what about factoring harder quadratic expressions? Quadratic expressions where the coefficient of x squared is not equal to 1. So what we always want to try to do is see if it's possible to factor out a greatest common factor so that we can get rid of that coefficient of x squared. But we can't do that here because 2 doesn't divide evenly into 11 or 13. So we're stuck having to factor this the hard way. Now this, honestly, I don't believe is that important. The only reason I show this to you is because A, you've learned it before and I want to remind you so you don't just lose it. And then also it could potentially show up on some standardized test. But if you think about this, the only reason that we ever really factor things is to find solutions to equations. And as you now know, having the benefit of having gone through Module 3, you know that if we were trying to find out, for example, when this expression equaled 0, we could just use the quadratic formula instead. We wouldn't have to go through the arduous process of factoring. But let's get a little practice. So this is a bottoms-up situation. Okay, remember how bottoms up works. Right, we're going to try to factor this. Bottoms up works much the same way as regular finding magic numbers did. We're going to calculate what the product of A and C is, and remember, we're just matching this to the standard form, ax squared, or the general form, we should say, plus bx plus c, where A is 2, B is 11, and C is negative 13. So A times C, it's always just going to be the coefficient of x squared times the constant, is negative 26, and B is 11. So we're trying to find magic numbers that multiply to AC and add to B. Well, what would those be? Numbers that multiply to give me negative 26 and add to 11. So I know that the signs are going to have to be opposite if they multiply to a negative. So I'm going to get a negative number and a positive number. And what could they be? I know that the positive one's going to have to be the bigger of the two. Well, it looks like it's going to be positive 13 and negative 2 are going to be my two numbers, right? Those multiply to negative 26 and add to positive 11. So then with bottoms up, what do we do then? So we're going to write this as our template, just like before, with x's, just like before. And we're going to start with our magic numbers. The only difference is now we're going to divide each of the magic numbers by a. Okay, and then we're going to simplify. So in the first case, 2 over 2 reduces to 1, and so that factor is done. X minus 1 is one of the factors. But in the second case, 13 over 2 does not simplify. So we're stuck with this 13 halves. If the fraction doesn't fully reduce, so I end up with a denominator, that's when I go bottoms up. Whatever the denominator is, I'm going to go bottoms up in front of the x, and that's going to change this factor to 2x plus 13. Really all that amounts to is I'm going to multiply, I'm going to distribute the whole thing, distribute a 2 through, multiply 2 by the whole thing. But you don't have to think about it that way. Just think about it, about the process as the 2 is going bottoms up in front of the x. And so our final answer is x minus 1 times 2x plus 13. Order doesn't matter. Order of the factors makes no difference. Okay. Okay, let's try one more of those. So how about here then? We've got, look for the magic numbers. Let's see, can I factor anything out? No, I can't, unfortunately. So 16 times negative 9 is negative 144, and then B is 18. So we have to find numbers that multiply to negative 144 and add to positive 18. So the numbers are going to be opposite signs, one negative and one positive. The positive one is going to be bigger, so let's put that one first. And what could they be? Boy, we'd have to just go looking for them. Factors of 144 that multiply to 18. We also know that the two numbers, if they add up to 18, and one's positive and one's negative, here's a trick I like to use. Most people would just, and this is fine to do, most people would just take 144 and break it up into factors and see which of those factors of negative 144 are going to add to 18. For example, if we took the factors positive 72 and negative 2, those would add up to 70, which is way too big. It's supposed to add up to 18. So you could just keep playing that game if you wanted to. Or you know that when you add them up, they have to add to 18. That means that the positive one is 18 bigger than the negative one. So what I would prefer to do, and if you like this, fine. If not, you can just keep making a list of factors over here. I just make a list of numbers where the positive one is 18 bigger than the negative one, and see which one works, which one multiplies to negative 144. So for example, let's start with how about 24 positive 24 times, let's see, negative, what would that be, 16? Or negative 6, sorry. Let's see, and that's going to be, that's it. What do you know? Got it. So positive 24 and negative 6. And if we had kept going with our list, we would have gotten to that. We would have had, for example, probably 36 and negative 3, and then we would have had negative 4 won't go into that. Never mind. Oh, yeah, well. Oh, no. Messed that up. It's 36 and negative 4. It's 3 times what? Oh, I gotta think here. 8, 48. Yeah, is that right? Yeah, 48. Now we could have just kept going down that list, and eventually we would have gotten to 20. In fact, it would have been the next one because 5 doesn't go into that. 24 and negative 6. Either way, those are our magic numbers, right? So that multiply to negative 144 and add to 18. So then we'll do bottoms up. So I'm going to get x plus 24 and x minus 6. And both are going to be divided by a, which is 16, both of the constants. So then what? Well, we got to reduce the fraction. So that's going to give us 24/16 reduces, let's see, 8 goes into 24 3 times and 16 twice. And then 2 goes into 6 3 times and 16 8 times. And so then I just go bottoms up for both factors. And we're done. So we should end up with 2x plus 3 times 8x minus 3. Okay, and maybe I'll just do one more. Okay, so what can we do here? Well, this one's actually by far the easiest of the group. Because look, we can find a number that divides evenly into all these. In fact, 8 goes into all of those, and because the leading term is negative, I'm just going to factor out a negative 8. So this is really simple. So we'll undistribute a negative 8, and then what's left over? Well, negative 8 times what is negative 8x squared? X squared. Negative 8 times what is positive 8x minus x, because negative 8 times negative x is positive 8x. And negative 8 times what is 96, and that's minus 12. Okay? Are we done? No, not quite, because now we've got a simple trinomial to break apart. So what's this equal to? Well, I've got my negative 8 out front. That's a factor. That counts, right? If we want to factor this completely, we need to include that. And then what does x squared minus x minus 12 factor into? Well, let's look for magic numbers that multiply to negative 12 and add to negative 1, negative 4, positive 3. Okay? And that's as far as we can go. So you know it's completely factored if I can't break it apart any further, but if I were to turn around and multiply it all back together, I would get the original answer. Okay, we got it.